In the last couple of videos, we looked at using limits to help us solve this tangent line problem, and we've done so, successfully. And we have two alternative definitions for the slope of the tangent line at a specific point. And let me just kind of remind you of those forms. So the first form of this limit definition is the limit as x approaches a, and the difference quotient in that instance is this: f of x minus f of a over x minus a. And then with a slight change of variable and some algebra, we came up with this other alternative form of this limit, and it's the limit as h approaches 0 of f of a plus h minus f of a all over h, right? And what we are able to answer with this, with either limit, is this problem. Again, you're probably getting tired of seeing my graphs, but I never tire of drawing them. So we have the graph of this function, and let's say my a is right here. That means the point on the graph would be right there, and then at that point we draw our tangent line, and the slope of this tangent line can be computed using either of these forms. Well, here's my question. And that's, if we are forced to use a limit definition, and at this point we are, right? We have no other alternative. Suppose instead of just being given one x value and you're asked to find the slope of that line, what if I gave you multiple points along this curve? So instead of a, now I'm going to use a subscript and say, let's say that's a1. In fact, let me switch back to, so a1, and then let's say I have a a2, and then a a3, and then an a4. So like, what if, for instance, let's say in one particular problem, you had 5 different points at which you wanted to draw the tangent line. So let's see, at this point right here, the tangent line would be something like that. At this point right here, the tangent line would be something like that. At this point right here, the tangent line would be something like this. And then right here, the tangent line would be, something like that. So the thing is, what if we wanted to find the slope of all these different tangent lines? If you think about it, either form that we would use, we would have lots of different limits to compute, because this a value would be different here, right? This would be different. This would be different. So yeah, it's almost like I'd be starting over another limit problem. They would all be indeterminate. You know how much we love those indeterminate limits. But they would all be different. So I would have to start from scratch every single time I do something like this. If I try this form, even though the h approaches 0, that pretty much is fixed. The a right here and right here would change. So therefore, whatever my function is, like if it's a polynomial, and I plug in the quantity a plus h, when I expand and simplify, I'll get a different numerator every single time, right? Well, what does that mean? It means we would be working, pretty much doing the same process over and over and over, going back to the start, setting up and simplifying our difference quotient, and then taking a limit, right? But there's a solution to that problem, and the solution is it's in part why we switched to this particular form, right? So the whole idea is now the point at which I want the tangent line to be, that varies. It changes, right? Because at every point here that I have highlighted on my x-axis, that's a different value of x. So it means that now I'll say this, my a is varying. It's changing, right? So because it's changing, maybe what I should do is, maybe I should just keep it as the variable x, right? So in other words, instead of plugging in the actual number here, since we now recognize that this number can change, why don't we just keep it as x, right? So this leads us to yet another form. So if you remember, like over here, we were saying, well, x is approaching a. Now what we're saying, suppose we switch back to x. Suppose we keep our a value as the variable x. In other words, don't plug the specific number in right now. Just keep it general, right? So as the variable x. What would that look like? Well, it's just a matter of changing the letter, right? But conceptually, it's an important change because, again, we're switching from a fixed constant to now a variable. So our limit would then look like this. We would say the slope of the tangent at any of these points now, right, would be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, again, provided the limit exists. Right, so provided this limit exists. So let's actually do this process before we say, and we have a lot to say about this, right? And in fact, the amount of things that we have to say will span several videos. But let's just see what the process would look like if we took this approach, right? So if we kept our function as it is, and also if we replaced the x with the quantity x plus h, and if we simplified and took a limit, we probably won't come out with a number anymore, right? We're probably going to come out with something that has an x in there. But let's see what it looks like with this example. All right. So let's start by using something like a quadratic. So let's try, I don't know, negative 2x squared plus 5x plus 9, right? So let's do it in stages. Set up the difference quotient and simplify and reduce as much as we can. Then take the limit, and then that, whatever we end up, that's what we're going to call the slope of the tangent line, right? Okay, so in fact, let's do it in stages. Let's just do one thing at a time. So I am going to do this piece first, right? So f of x plus h. And again, it's very important that we interpret this expression correctly. And what this is saying is replace x with the expression x plus h. This is not equal to f of x and then add the h after. This is basically saying you add the h to your x before you plug it into your function. This is saying, remember that we often refer to this as y. So what we would be doing is we would be adding h to the y value, and that's not what this is saying, right? So unfortunately, this is a common mistake that occurs, but no, we won't do that. Right, well, let's do what we are supposed to do. So we're going to take negative 2 and then wherever there's an x, replace it with x plus h. So then it looks like this. Same thing, wherever there's an x, replace it with x plus h. And then we have to expand and simplify and, make this as simple as we can, because then we have a few more algebraic operations to do. By foiling this out, we're going to get x squared plus 2xh plus h squared. And let's distribute the 5, so that's 5x plus 5h plus 9. Also, let's distribute the negative 2. Negative 2x squared minus 4xh minus 2h squared plus 5x plus 5h plus 9. And you look at this and you're like, please let there be something in common, something that we can simplify. But none of these terms are like terms, right? So we just have to leave it as it is. So that's what just this part in blue is, right? So now let's do the entire numerator. Let's take what we just got and then subtract the original function, right? So then let's give ourselves some room here. So f of x plus h minus f of x. So all of this is f of x plus h. So minus 2x squared. In fact, let me go ahead and put these in, I'll use square brackets. So minus 2x squared minus 4xh minus 2h squared plus 5x plus 5h plus 9. So that's, again, just the first term in the numerator. Now let's subtract the original function. So minus negative 2x squared plus 5x plus 9. Well, what tends to happen? Well, in fact, so now to drop the first pair of square brackets, I don't need to do anything special. Right, so just write that entire expression, pretty long expression. Now to drop the second pair of brackets, I have to distribute the negative. So that becomes a positive 2x squared, and then a minus 5x, and then a minus 9. Now when I look to find some like terms, I do see some like terms. So for instance, there's a negative 2x squared, and then a positive 2x squared. Here's another pair, a positive 5x and a minus 5x. And then a third pair, a plus 9, minus 9. So all those things in green, they'll cancel out. And if you notice, what's interesting about this part of the problem, all the terms that cancel out don't have an h. Right? Everything that I have circled in green, they don't have a factor of h. Right? They're either purely constant or just an x term or an x squared term. So that means everything that's left will have an h. So this is what the numerator simplifies to: negative 4xh minus 2h squared, and then plus 5h. All right. So that's the long part of the process, but we got the numerator simplified. Now I'm going to go back and set up the entire, so I'm going to switch back to my regular white marker here. And we're going to set that entire thing up. So take what we just obtained and put it all over h, right? Right, so f of x plus h minus f of x over h is this expression divided by h. And this is where we have to factor and reduce. And in this case, what happens is the h, there's a common factor of h in the numerator, so I can factor out an h. That leaves a negative 4x, and then a minus 2h, and then a plus 5 in parentheses. And I still have that factor of h in the denominator. So now I can reduce it, and it simplifies even further. Negative 4x minus 2h plus 5. All right. Now, so now that we've done the algebra part, now we do our limit calculation. So remember what we're doing now. We're saying that the slope of the tangent line is equal to the limit as h approaches 0 of this new form where I don't plug in a constant in, but I just keep the variable x, right? And we simplify this entire difference quotient, and what that difference quotient simplifies down to this. So that's the limit I have to evaluate. So we have our negative 4x minus 2h plus 5. When I use my algebraic properties to evaluate a limit, I'll plug in h equals 0, and I have negative 4x minus 0 plus 5. So the slope of the tangent line is this. It looks like we have another function because we still have the variable x, but it's negative 4x plus 5. All right, so let me just kind of summarize what we did. We just said this, remember we took the quadratic. It was that negative 2x squared plus 5x plus 9. So for this parabola, the slope of the tangent line is negative 4x plus 5. So how do we make sense of this when we didn't have a specific point? Well, basically, what we're saying is now, I'm just going to sketch this parabola. And now I know that this parabola opens down because the leading coefficient is negative. Now I don't know if it has roots. We could check to see if it has. Actually, yeah, it has 2 real roots. So what I will do is I'll just put the x-axis here, right? So wherever those roots are, they're somewhere. But let's, for instance, say this was my number line. I had a 1 there, and then let's say a 0 there, and let's say a negative 1, and a negative 2, and then a 2, and so forth. So, for instance, if I were to plug x equals negative 1 into this function, it would give me the y value at that point. Now, if I were to plug negative 1 into this function, it would give me the slope of the curve at that point, right? And that's the whole idea now, is after going through the limit process and coming up with not just a constant that represents the slope at one point, I now have a function that can give me the slope at all these different points. As long as this function is well defined, as long as I can plug in my x and get a number, that number will represent the slope of the tangent line at a specific point. In fact, let's do this. I'm going to take my graph off and pretend that I don't even know what the graph looks like. I have no idea. Oof, it's gone. What I could say now is this. In fact, we can make a table. We can make a table that you pick an x, I can tell you what the slope of the tangent line is going to be. So let's do this. I'll make a table with the a column with just a few x values, and then the corresponding y. And we know how to complete this part of the table. If you pick an x, we can find the y. But now I'm going to say I can also find the slope of the tangent at that point, right? So let's do this. Let's pick a negative value for x, and then 0, and then a positive value. So let's start with something like -1. If I plug -1 in here, I'm going to have -2 minus 5 plus 9. So this gives me a y value of 2, right? If I wanted the slope of the tangent line at this point, now I could plug my x value and plug it into this function. So it would have a slope of 4 plus 5, which is 9, right? There you go. So for instance, what we would have is we would have the point on the graph would be -1, 2, and the slope at that point would be a positive 9. And then if we wanted to actually write down the equation of the tangent line, so the tangent line equation, I'll just write it in using the point slope form, but now it will be y minus the y value is equal to the slope times x minus the x value. And again, I'm not even going to simplify it right now. I just want to show you, once we've done this limit calculation with the variable x instead of a specific number, you give me any x that works. And by works, I mean is in the functions domain and also in this expressions domain, right? What if we try x equals 0? Well, if we plug 0 in, so we'll end up with 0 plus 9. So now the y value is 9. And then I'll have a different slope. The slope would be 0 plus 5. So it would be a positive 5. Different point, different slope. And then let's try another one. Let's say x is equal to, I don't know, 3. So if we plug 3 in, let's do it in the function to figure out the y value. It will be, what's that, 9 times -2, so that's -18, and then plus 15, and then plus 9, so that's 6. So when x is equal to 3, y is equal to 6, and the slope of the tangent line at that point is -12 plus 5, and now we get a negative slope, right? And let's just for completeness fill out this table. So the tangent line at the point 0, 9, its equation, y minus the y value is equal to the slope of 5 times x minus the x value. And then at the point 3, 6, the tangent line's equation is y minus 6 is equal to, now your slope is -7, and then times the quantity x minus 3. Right? So now we've actually found a way that, okay, if we have to do this process multiple times for a single function at different values of x, it's like we do the limit calculation first in a general way with our variable x, like we did right up here, and then do our limit, and we come up with now an expression or a function that gives us the slope of the tangent line at all these different values of x that we can pick, right? And the name of this function, right, that we've been using to compute the tangent line slope is called the derivative, right? So the function Because it is a function. If you look at it, in fact, it's a linear function, negative 4x plus 5. It just gives us a different bit of information. So the function, and I'll use this particular word, derived from y equals f of x, right? It started out this way. Derived from y equals f of x via our limit, right? Let me write down that limit, our most recent one, right? So this function that we derive from our original function using this limit is called the derivative of y equals f of x. So it's called the derivative of y equals f of x. So provided this limit exists, we have to keep saying that because we know limits don't always exist, and we'll look at some clear-cut instances where we can tell, even just by looking at a graph, when this limit won't exist. But for now, we're introducing a very important word and a very important process, right? That's associated with some function, but now this process, what it produces is another function that gives us our slope of the tangent line. And it's so important that it even has its own notation, right? We denote the derivative of f of x as, we still use the letter f, but we put a prime there. We call it a prime of x. So we're basically saying that they are related. In other words, we get this by doing a particular process to this. So that's why we use the same letter, but we use the prime to indicate, yep, there's something significantly different. Even though they are related, there's a key difference between this function and this function, right? Now, it turns out there's another notation for it, and let me introduce that notation as we're gonna wrap this up. Now, going all the way back, when we first started talking about rates of change, and it feels like forever now, there's so much that's happened since. But when we were doing the rate of change, remember one formula or one symbol that we wrote down for the slope of the secant line? That was delta y over delta x, right? Well, it turns out this limit here can be expressed in terms of deltas, right? Because again, it's still, if you take away the limit, if you just focus on the difference quotient, that's still just a rise over run. It's a different way of writing it, right? But this leads to this particular notation. So for instance, this right here can be denoted as the change in y. And if I replace h with delta x, so the change in x, so if I call this delta x and then this also delta x, this whole limit looks like this. So it's the limit as delta x approaches 0 of delta y over delta x. So this is another way to write down what we just did, right? Basically, instead of using h, we can use delta x, and then the numerator here is your change in your function value, so that would be your delta y. So because this limit can be represented like this, the alternative notation for the derivative is basically saying with all these deltas, and deltas are getting smaller, the delta x is approaching 0. A German mathematician, Leibniz is his name. He came up with this idea of replacing all of this, right, with dy over dx, right? And d, obviously, delta is the Greek letter for d. So he decided to just write all of this as dy over dx. And this is an alternative notation for the derivative. And we will use both of these. I can't even imagine how many times we're going to use it, but many times we're going to use the prime notation or this Leibniz notation. So Leibniz notation. Right? So let's just kind of summarize, and we have a function y equals f of x, and when we apply this limit, so the limit as h approaches 0 of f of x plus h minus f of x over h, as long as this limit exists, we're now going to get a new function which is denoted either that way or that way, and it is called the derivative, right? In fact, it's the derivative of y equals f of x. And what does it give us? It gives us the slope of the tangent line at any value of x at which this is well defined. So let's write that, and that's the perfect place to stop. So f prime of x gives the slope of the tangent to f of x at any value of x at which it is defined, right? So at all values of x for which it exists, right? And this is a huge step forward, not just, visually, just getting used to these symbols. Conceptually, this idea of a derivative, like you do a process to one function and you create this other function, and right now this function, it gives us this key bit of information, the slope of the tangent line, right? So what we will certainly do a lot more examples of this, and then explore what are some of the bad things that can happen. So what can go wrong in this process, right? Because we keep saying provided the limit exists. So what does it look like when the limit doesn't exist? Well, if you're interested, tune in to the next set of videos. See you then.